Hi guys, we are the Snail Squad, and today we'll be discussing the application of differential equations to examine the effects of rising temperatures on snails in a tide pool. You might be asking, what exactly are we talking about? So let me briefly answer that. We will be looking at snails in a tide pool. Snails are a type of mollusk that has a soft body and a hard shell for protection. Snails, along with other small marine life, often get trapped in tide pools, which are formed by water getting trapped in crevices when tides recede. Since tide pools are generally very shallow and small, the sun is able to heat the water in the pools much quicker than the ocean. This, of course, has some significant effects on the sea life that reside in the pools. For example, when the tide pools form, sea snails and other inhabitants must endure long hours of sun exposure, as well as increasing water and body temperature. This is the phenomena that we will be exploring. Before we begin, it is important to mention previous research performed that provides us with insight into the topic. Vinagre, Mendonca et al. Examined the thermal limits of coastal species and found that most of the tropical species had upper limits below the maximum temperature of the habitat, except for 3 gastropods, including 2 species of sea snails. Another paper by Graham Robert Paul Brown Lee suggests that 2 types of sea snails have inherently different lethal and sublethal responses to temperature, but are similarly inhibited by extreme temperatures. Additionally, it is especially important to study the effects of temperature on sea snails, as well as all marine life, because of our current status of climate change. As global temperatures rise, so will the oceans. The basis for our research on this topic comes from the SIMIODE Research Project by the same title. All of our numerical data comes from this project.
Before we dive into our model, here's a quick review of our topics of focus. As the tides rise and fall, tide pools trap various sea animals, including snails, in uneven areas of rocks and sand. The small volume of the tide pools causes the water to heat much quicker than that of the ocean, causing the sea life to experience higher than normal temperatures for a period of time. Additionally, it is important to mention that snails are ectothermic organisms, which means they are cold-blooded and cannot regulate their own body temperature. Their body temperature matches that of their environment. Therefore, we assume the temperature of the snail to start at the initial water temperature of the ocean. These snails, trapped in a tide pool, are then exposed to the rising temperatures and direct sunlight for approximately 3 to 4 hours at a time. We are going to use differential equations to model the change in the snail's temperature, as well as to determine whether the snail will reach its upper lethal body temperature while in the tide pool.
To begin, we will create an initial model that demonstrates how water temperature changes with time. We will use experimental data that was collected from a simulated tide pool. The water temperature in degrees Celsius was collected over a 60-minute time period, as seen in the chart. When the data is graphed, it is shown that as time increases, temperature increases. After creating a line of best fit with the data points, we can find the slope. The slope of this line represents the rate of temperature change, which is equal to 0.107 degrees per minute. Now that we have our rate of water temperature change, we can solve the differential equation. This differential equation is our model to show how the temperature of the tide pool changes with time. Our initial temperature is the temperature of the water when T equals 0, which, according to our experimental data, it is 28.7 degrees Celsius. When we plot our solution from our differential equation with the experimental data, we can see that the equation for T is reasonable to model water temperature with respect to time, since it is very similar to the experimental data. Their y-intercepts, which represent the initial temperature of the tide pool water, only differ by about 1.4 degrees Celsius.
Next, we will be modeling the body temperature of the snail. We first need to make a note that the lethal body temperature of a snail is between 40 and 45 degrees Celsius. This means that if the snail were to reach those body temperatures, it may lead to death. It should also be noted that the typical water temperatures in the summer months for the mid-Atlantic coast range between 23.9 and 29.4 degrees Celsius. For our model, we will assume that the snail's body temperature matches the surrounding water temperature in the tide pool. The mathematical model for a snail's temperature is very similar to the model we created earlier for water temperature. This time, our model shows how the snail's body temperature changes within time. Once again, W represents the rate of water temperature change, T represents the time, and T initial represents the initial starting temperature of the tide pool water. One question we can ask ourselves is, when will a snail reach its upper lethal body temperature? Using 40 degrees Celsius as the snail's upper lethal body temperature and 29.4 degrees Celsius as the initial starting temperature of the tide pool, which is based off of the mid-Atlantic coast, we can find that it will take 99.07 minutes for the snail to reach its lethal body temperature. Another question we can ask ourselves is, what is the maximum initial water temperature for a snail to survive in a 4-hour tide pool? Based on our model, where 4 hours equals 240 minutes and 40 degrees Celsius is the lethal body temperature, we can conclude that the max initial water temperature can be 14.32 degrees Celsius. This means that the initial water temperature must be less than or equal to 14.32 degrees Celsius for a snail to survive 4 hours in a tide pool. However, based on the summer mid-Atlantic coast temperature range of 23.9 and 29.4 degrees Celsius, the maximum allowable initial temperature is never reached. Thus, based on our model where the snail's temperature matches the water temperature, the snail will never survive 4 consecutive hours in a tide pool in the mid-Atlantic coast.
You might be wondering, doesn't the shell protect the snail from the heat? And if you are, then you may have a point. Our original model assumed the body temperature of the snail would match that of the water. However, the snail's shell will actually work as an insulator, and therefore their body temperature likely changes at a different rate than the tide pool water does.
Our last model will examine this phenomena and the role of the shell as an insulator. So now we'll model a snail's temperature with their shell's insulation. To create our model, we need to understand Newton's law of cooling, or in our case, heating. This law states that the rate of change of temperature of the snail is proportional to the difference between the temperature of the water and the temperature of the snail. Looking at the formula for Newton's law of cooling, the temperature at any time t depends on the temperature of the surrounding environment, represented by T sub s, the initial temperature of the object, represented by T sub 0, the constant rate of proportionality, k, and time, t. Using S of t to represent the snail's temperature and Newton's law of cooling, we can create the following differential equation to represent the snail's temperature with shell insulation. The differential ds dt equals our constant rate of proportionality times the temperature of our water minus the temperature of the snail. And we can simplify this further by plugging in our previous equation for the temperature of the water. Solving this differential equation using the fact that the initial temperature of the snail is assumed to be the initial temperature of the water, we can get our new mathematical model for the snail's temperature at any given time. Small t is our variable, and w, k, and t naught are constants. Now that we have our mathematical model to represent the snail's temperature with shell insulation, we can solve for k, the constant rate of proportionality. During the snail experiment, it was determined that after 51 minutes, the temperature of the snail was 33.6 degrees Celsius. We can plug this into our model S of t and solve for k. We found that k equals 0.192101. This constant depends on the properties of the material. In our case, the material is the snail's shell, which is mostly calcium carbonate, a compound found in many rocks. Now we can put the temperature of the snail together with the water. By graphing our water temperature model in red and our snail temperature model with the shell insulation in blue, you can see that the snail's temperature is slightly less than the water's temperature. This means that the snail's shell is providing sufficient insulation. When we set the snail temperature equation equal to 40 degrees Celsius, which is the snail's lethal body temperature, it can survive in a tide pool for 110.8 minutes, about 2 hours. Unfortunately, for a tide pool of 3 to 4 hours, it seems that the snails won't survive. However, there are likely other biological factors to be taken into consideration so that the snails aren't constantly dying.
To finalize our presentation, we will end with some points of further discussion to think about. In our presentation, we have discussed all the different models to portray both the water and the snail's temperature. One question we want to ask our viewers is it realistic to assume the water temperature increases at a constant rate for the entire duration of the tide pool? Think about what factors affect water temperature. In addition, suppose the water temperature in the tide pool levels off after a certain time. What conditions on T of t, which is the water temperature at time t, would be needed for the snail to survive in this case? Keep in mind Newton's law of cooling. Thank you guys for watching. We hope you enjoyed our presentation and learned something interesting. Feel free to comment below with questions or suggestions for future research. Have a great day. Wishing you all the best, the Snail Squad.